Properties of monosaccharides. Carbohydrates are called sugars because they have a sweet taste. The degree of sweetness varies as shown in table 11.2 down here on the bottom left. For instance, fructose is about 73% sweeter than sucrose, and sucrose is just regular table sugar. All carbohydrates are solids at room temperature, and because of the many hydroxy groups on the molecules, monosaccharide carbohydrates are extremely soluble in water. And you know this if you've ever tried to dissolve sugar in water, it dissolves very easily. The hydroxy groups form many hydrogen bonds with the surrounding water molecules. In the body, this solubility allows carbohydrates to be transported rapidly in the circulatory system. Here's kind of an interesting idea if you like to chew gum, which is this molecule here, xylitol. It says here that most chewing gums are sweetened with sugars that can cause cavities. However, xylitol is the only sweetener that has been shown to reduce potential for tooth decay. So maybe I need to develop some kind of gum with xylitol in it. Anyhow. Now, open chain forms of monosaccharides exist as aldehydes or hydroxyketones that we already saw, and those are readily oxidized by weak oxidizing agents due to the presence of adjacent alcohols in the carbohydrate structure. Sugars that can be oxidized by weak oxidizing agents, we call those reducing sugars. So they the sugar is oxidized, but when the reaction happens, the oxidizing agent gets reduced. So again, sugars that are oxidized by a weak oxidizing agents are called reducing sugars because they cause reduction. Thus, all monosaccharides are going to be reducing sugars. We can test for the presence of a reducing sugar in a lab using what's called Benedict's reagent, which is a mild oxidizing solution containing copper 2 ions, and copper 2 ions are blue. And as the open chain form of the monosaccharide is oxidized, the copper 2, which is blue, is precipitated as copper 1 oxide, and copper 1 is a red-orange solid. And you can see the example here. So again, copper 2 is blue, okay? Then we have our aldehyde here. You see it's being oxidized to give us a carboxylic acid, right? Gaining oxygens. And then here we have copper 1 oxide, and copper 1 oxide is a red precipitate. So it's just a qualitative test. You can see it with the naked eye. And so again, you need to know what the Benedict's reagent is. And this is Benedict's reagent here. You can see it's got this blue color to it because it contains copper 2 plus ions. But when the reducing sugar gets oxidized, right? So the sugar gets oxidized, what happens is that the copper gets reduced from copper 2, which again is blue, to copper 1. And you need to know here, this is copper 1. So we would call this copper 1 oxide, okay? And that gives you a red-orange precipitate. So you can see here, the addition of Benedict's reagent from the first tube produces colors due to the red copper 1 oxide that indicate the amount of glucose present. So this is an experiment we do oftentimes in the lab with students where they learn how to test for reducing sugar. And so they just add the Benedict's reagent. Normally you have to heat it up. So you put it in a boiling water bath and then it turns red, and then you know sugar, right? Reducing sugar present, right? Just a chemical test for the presence of sugars. And Benedict's reagent actually used to be used to detect the amount of glucose in urine of people who are diabetic. The hydroxy groups of monosaccharides can behave as alcohols and react with acids to form esters. When the central carbon atom of an ester is replaced by a phosphorus atom, the new functional group is called a phosphate ester. And you see the structure of the phosphate ester here. Esters formed from phosphoric acid and various monosaccharides are found in all cells, and some serve as important intermediates in carbohydrate metabolism and as backbones to other biomolecules. The structures of two representative phosphate esters are shown here. So we have glucose 6 phosphate, and if you've studied any biochemistry before, you might know that this is called G6P. And then we have fructose 6 phosphate, which is F6P, like that. But you can see that we have our phosphate ester here on the glucose 6 phosphate, and then we have our phosphate ester over here on glucose 6-phosphate. And the phosphodiester bond connects deoxyribose and the phosphate groups that make up the backbone of DNA. And you can see that shown right here. Okay, this is how we connect the backbone of DNA with these phosphate esters. Now, if you remember from video 11.3 and section 11.3 in the textbook, that hemiacetals and hemiketals can react with alcohols and acid to yield solutions of acetals and ketals, respectively. Thus, cyclic monosaccharides, or hemiacetals and hemiketals, react readily with alcohols in the presence of acid to form acetals and ketals, right? Just like we saw before. However, now we change the name, and so the general name for these carbohydrate products is glycosides. So the reaction of alpha D-glucose with methanol is shown here. So here we have our hemiacetal, right? We have carbon, oxygen, hydrogen, carbon, oxygen, carbon. So that is a hemiacetal. We react it with some methanol in the presence of acid, and we end up with a mixture of alpha and beta methyl glycosides. So again, when you have an alkyl group on your anomeric carbon oxygen, we call that a glycoside. And so the bond that leads to the oxygen here now, we call that a glycosidic bond. So you have to know what a glycoside is. Again, all you're doing is replacing OH with some kind of OR group, and then it's called a glycoside. And again, what you're doing is you're converting a hemiacetal to an acetal. Now, the hemiacetal in glucose is located at carbon 1, the anomeric carbon, and so the acetal forms at that same position. All the other hydroxy groups in glucose are ordinary alcohol groups and don't react under these conditions. So that's why all these hydroxy groups, like this one, oops, where's my highlighter? Like this one, this one, this one, this one, right? Those don't react under these conditions. So as the glycoside reaction takes place, a new bond is established, like I said, between the pyranose ring and the methoxy group. And the new group, like I said, can point up or down. So we end up with a mixture of alpha and beta glycosides. And like I said before, I'm repeating myself a lot here, that the new covalent bond between the carbon and the oxygen that joins the OR group, and in this case, it's an OCH3 group, is called a glycosidic bond or a glycosidic linkage. Now, although carbohydrate cyclic hemiacetals and hemiketals are in equilibrium with open chain forms of monosaccharides, the glycosides are much more stable and don't exhibit open chain forms. Therefore, glycosides of monosaccharides are not reducing sugars. So if you're ever asked, if you're ever shown a glycoside like one of these and somebody says, or somebody asks you, is this a reducing sugar? The answer is no, because it doesn't contain a hemiacetal anymore. Now, what you're going to see later on in section 11.7 and 11.8 in the textbook is that both disaccharides and polysaccharides are examples of glycosides in which the monosaccharide units are joined together by acetal or glycosidic bonds. All right, let's take a look at this example. 11.7 deoxyribose is a component of DNA. A modification of deoxyribose is shown here. Highlight any acetal or ketal group and use an arrow to identify the glycosidic bond. Well, first of all, we can identify the glycosidic bond very quickly, right? This is carbon 1 here. This is carbon 1, and so this would be the glycosidic bond. And you can see that we have an acetal here, right? If we go from the red carbon, I'll use my yellow highlighter. We go carbon, oxygen, carbon. And then if we start on that yellow carbon again, carbon, oxygen, carbon. And so this whole area here, that is our acetal. Acetal, right? Because remember, if you have a carbon with an OR group on it and another OR group on it like this, okay, this would be an acetal.